Hey everybody, Dr. Retzek here with you. This is our 7th video in Calc 4, and it's a short follow-up on chain rule. So we're still in section 14.4, and really we have 2 tasks today. So this is still section 14.4, and this is a continuation of our discussion on chain rule. The first thing that we'd like to do today is try to give a visual, geometrical sense of what chain rule might be doing. So I wanted to draw a picture and talk about the connection between the branch diagram and what's really happening on the picture. So imagine a surface like this. It's our classic flying carpet. That is z equals f of xy. And I want you to imagine it floating right above the origin. So the z-axis actually is right in the middle here. So that's z pointing up, and then it pierces the surface. Can't see it for a sec, and then it comes down like this. And then here's the y-axis, and then here's the x-axis. So it's a classic picture. Only in this picture, we are only considering points on the surface where x is cos t and y is sine t. So we're looking at the surface, but x and y, which are the independent variables for z, themselves depend on t. So what that means in the picture is that down there flat in the xy plane, x and y can't be anything willy-nilly. In fact, you guys recognize those parametric equations, x equals cos t and y equals sine t, as tracing out a circle centered at the origin of radius 1 down there flat in the xy plane. So that's the circle flat down there. X squared plus y squared equals 1, living flat in the xy plane, and it's being traced out in this direction. And so maybe here's t equals 0, and then here's t equals pi over 2. It's our classic drawing from last quarter down there as far as the xy plane is concerned. Now, if you're plugging those x comma y's off that red circle into the surface, then the path on the surface corresponding to those inputs is some sort of wonky closed loop. But you know, the surface is this kind of wavy, weird flying carpet thing. So the closed loop maybe looks like this, say. Who knows how that surface looks? But those are the outputs that go with these inputs. Now the branch diagram that goes with this situation looks something like this. You see that z depends on x and y, but each of x and y depends on t. So our little branch diagram looks like that. So in the end, on that path on the surface, this path right here, this red one on the surface, z really only depends on t. You tell me a t, that's going to make x and y equal to something, and that x and y will make z equal to something. So in that sense, z only depends on t. And so the chain rule that goes with this picture is the regular old, good old-fashioned Calc 1 normal d's derivative of z with respect to t is equal, by chain rule, and by our branch diagram right here. Think of the ways a change in t can affect z. There's really 2 branches. It's the partial of z with respect to x times a regular old dx dt plus partial of z with respect to y times regular old dy dt. The chain rule there enables us to compute dz dt, and the picture is telling us what that computation really is. Look at this expression here. That stands for z's rate of change with respect to t. So that's telling you how fast the altitude is changing relative to changes in t. Changes in t send you around to that red circle flat in the xy plane. So it's telling you something about your change in altitude on this hike relative to t. So it's some sort of rise over run, but it's just rise over run on that hike, on that surface. It's telling you a little change in z over change in t, like right here, say, at this moment, it's telling you a little change in z over change in t. Anyway, it's not just symbol pushing with chain rule. It actually represents something visually, and it's just a change in altitude per change in t. If you think of t as time, then this is going to be measured in your altitude changing in feet per second or something like that. Anyway, just a visual to go with chain rule and to make it feel like we're not just pushing symbols around with those branch diagrams. The second important thing that we're trying to accomplish today is actually different, and it gives us a new powerful tool to compute some derivatives that were a little annoying the first time we developed the tool. So I want to look at an example. And in this example, we have the expression xy plus z cubed x take away 2yz equals 0. And you guys will recognize that expression as the one I messed up in the second video for 14.3. In the follow-up video for partial derivatives, where we did the example with implicit differentiation and I messed up the algebra, and then at the end I messed up the plugging in of the 0.111. This is that example. And I bring it up here again because the technique we're about to develop, I think, might have prevented the algebra errors that I made. And so is handy for you guys to have too, because it really cuts down on the algebra when you're doing implicit differentiation. Okay, so remember what we're doing. This is some kind of a surface. I have no idea what this picture looks like, but if you specify an x and a y, that will force z to be something. For example, if you specify x is 1 and y is 1, then you get z cubed minus z is 0, and that tells you z has to be either, what, 0 or 1. Oh, or minus 1. Yeah. In any case, this thing is a surface. Choices of x and y dictate values z. So in that sense, z depends on x and on y. Okay. You could just immediately launch into this and start doing implicit differentiation like that old example I messed up. This is offering us an alternative, which amounts to the same thing. Here's how the alternative works. Call the left-hand side of that expression big F of x, y, z. After all, it's just some big mess with x's, y's, and z's in it, so give it a name. That's big F depending on x, y, and z. And you can see that big F is literally equal to 0. Big F is constant. It looks like it's not because it's got all these letters in it, but look at the other side of the equal sign. This just comes out to 0 everywhere on this surface. Big F is constant. Think of this even as the level surface that goes with the function big F and output value 0. But however you think about it, just name it. Name the left-hand side. Okay, so big F depends on x, y, and z. Big F depends on x, y, and z. But you see, we're thinking of z as depending on x and y. Z is implicitly a function of x and y. And x is just a function of x. And I know that looks crazy. X depends on x, no kidding. And y is just a function of y. And z is a function of x and y. So we're kind of shoehorning this branch diagram idea into thinking about big F. Big F depends on x, y, z. X depends on x, y depends on y, and z depends on x and y. Now, if you take that branch diagram and you get interested in, say, big F's partial with respect to x, let's say. Let's say ultimately we're interested in big F's partial with respect to x. So we're curious how big F depends on x. Well, it looks like there's two branches. That changes in x can propagate back through to affect big F. So if you're just blindly doing chain rule, then I think for sure we would say, okay, well, big F depends ultimately in that bottom row on x and y. We're interested in its dependence on x. So let's do some chain rule. So partial of big F with respect to x equals, okay, now there were two branches. Partial big F with respect to x times dx dx plus partial big F with respect to z times partial dz dx. Now make sure you know which branch produced which of those pieces. This piece right here goes with this branch right here. This piece right here goes with this branch right here. And those are the only two branches that a small change in x can propagate through to affect F. All right, now let's clean this up some. It looks a little weird to me because I feel like I see df dx in two places. Look at this notation. On the left side of the equal sign, we're talking about big F's partial with respect to x in terms of the x's all the way at the bottom of the diagram. On the right-hand side, right here, we're talking about big F's partial with respect to x in this part of the diagram. So even though we use the same symbol, you have to sort of interpret them differently as far as the diagram goes. But it's never going to matter in the end, because on the right-hand side, we can keep using that notation. Derivative of x with respect to x is just 1. And then this side goes unaltered. And on the left-hand side, this is the beauty of it. On the left-hand side, don't forget what big F equaled in the first place. Big F is constant. It's just a mirage. The left-hand side is a total mirage. Big F is constant. big F is 0. Therefore, big F's derivative with respect to any letter is 0. Now, this line right here, this is really easy to solve for dz dx. Therefore, dz dx equals negative df dx over df dz look back at what big F was right there. Look back here, right up here. Let's find df dx. So what is that? Just a y plus z cubed? And let's find df dz. What is that? 3z squared x, take away 2y? And that's exactly the answer we got when I botched this problem the first time, when we did sort of, regular implicit differentiation. Only now we cut straight to the chase. And the point is this: you aren't going to reinvent this wheel every time you encounter this situation. You are going to cut literally straight to here. As an example, what if instead you had been interested in dz dy? Then dz dy equals, bam, straight to the blue box, negative df dy over df dz, denominator the same. Come back up here, look at df dy. So what is that? X, take away 2z. Done. Look at that. That problem took 30 seconds. Because you can always cut straight to the blue box. But we couldn't have said that 2 days ago, because 2 days ago we didn't know chain rule. Quick caveat on those blue boxes. In those blue boxes, take care. Those blue boxes are crazy talk if you're at a point where that denominator is 0. So at any point where that denominator is 0, this makes no sense. But at any point besides those, this is a quick way to get here and here. Bam, straight to it. And that sort of circumvents all the crazy algebra that sometimes arises during implicit differentiation. Okay, that's it for chain rule. If you guys get the branch diagrams and you remember these 2 blue boxes just to save you time on implicit problems, then you are officially certified in section 14.4. All right, see you next time.